Good morning. I'm Naoyuki Takaki from Tokyo City University. I talk about breeding capability of Moltex stable salt reactor. This time, I am only one participant from Japan, so I'd like to touch very briefly recent movement on thorium or MSR research in Japan. And I talk this. New strategic energy plan was released this summer. Yes, July 3rd. The Japanese cabinet approved fifth strategic energy plan that will guide the national energy policy going forward to 2030 and beyond. And it refers to the renewable energy. It says it's a core power source in Japan. And it also continues to position nuclear power as an important base load power source. And Japan will maintain the share of nuclear as about 20% in 2030. This is a share of energy source in 2030. Oil, 3%, coal, LNG, nuclear, and renewable. These two have similar number. And in the renewable energy, main comes from hydropower and solar, PV, and wind biomass. This is the strategic plan, and in this it is Japanese, but you can see it refers molten salt reactor for the first time in chapter 3, promotion of technology development. This is means molten salt reactor. This is the very first time Japan government officially touches MSR. And in this plan, it says there are several technical challenges to be pursued. One is, yes, LWR technology improvement. This is the first priority. And it also says innovation is necessary to improve safety, reliability, and efficiency of nuclear energy. And to promote this with strategic flexibility, the cabinet shows visions and keeps watching on small modular reactor and molten salt reactor development progressing in US and EU. So it's not a direct expression. Japan will develop MSR, no, but it keeps watching. Very indirect expression. This movement was driven by some representative of Liberal Democratic Party, steered up by some enthusiastic thorium evangelists. And this seems to affect decision by ministries of finance, Ministry of Industry, Ministry of Education for building budget for MSR study. So the situation is changing. This picture shows the International Forum on MSR was held at Members Hall of the Democratic Party on June. And you can see some known faces, presenters invited from ThorCon, Elysium Industry, and SINAP. More than 200 participants from nuclear industry in Japan. So this forum was held this year and last year. So the atmosphere is gradually changing. And activities in Atomic Energy Society of Japan. From 2010, there was a working group on utilization of thorium fuel in LWR and FBRs. but this workshop was focused on only solid fuel. And from 2013, Specialist Committee on Spreading Out of Molten Salt Technology to Nuclear Energy. This is my translation, but you can catch the meaning. Development of MSR, molten salt technology to nuclear energy. Headed by Professor Yamawaki. You saw him on a movie on the first day, the thorium documentary. Yes, he's a committee. And this summer, new committee was opened, thorium nuclear energy system, by me. And there are more than 40 members from manufacturer, utilities, universities, institute. The purpose of this committee is following up on world trend and comparison between uranium and thorium system from scientific and engineering viewpoints. Then a proposal for how Japanese strategy for thorium R&D, including MSR, ought to be. I'd like to propose this in 2 years. Okay, why breeder? This is very maybe obvious for you. The conversion ratio or breeding ratio, if once the value exceeds 1, resource utilization factor drastically improved like this, 60% or more. It depends on the how much you have recovery loss. Smaller recovery loss means higher resource utilization factor. And once the breeding ratio exceeds 1, the resource utilization factor depends on the average burn-up. This is a Monju target. But the Monju it was not designed to recycle minor actinides. And the recovery loss is more than 1%. So the utilization factor was like this. And the new Japanese sodium first reactor project targeted around here. And what I want to say here is breeding with closed cycle is essential for maximizing resource utilization and minimizing waste, regardless of uranium or thorium, solid fuel or liquid fuel. This is closing cycle, and breeding is essential. And I studied the breeding capability of Moltex stable salt reactor. They said sometimes static molten salt reactor. Anyway, it's SSR. They use salt, fluoride salt for coolant, chloride salt for fuel. And they are separated by cladding. Inside cladding, chloride fuel salt exists. And the fuel assembly is similar to light water one. This concept was proposed by Dr. Ian Scott. And he visited Japan two years ago, and last year I visited him, and I talked to him. I'd like to check the breeding capability, because he said, there was a presentation first day, this conference. This reactor can be designed as a burner and a breeder, SSR, W, or yeah. So there are several versions. And then I'd like to follow their calculation. This is a core specification. These values and the compositions of salt were, I referred Moltex paper, 40% fuel salt and 6% sodium chloride. Plutonium enrichment is here. And Yes, and I don't change anything from their original design, but I use the fuel PRU composition like this. It was taken from values for light water reactor spent fuel. This burn up the 4 years cooling, after 4 years cooling. And it includes not only plutonium, but neptunium, some neptunium, americium, curium. Methods. First, we done with some calculation with pin cell, then full core calculation using continuous energy Monte Carlo code MVP developed by Japan Atomic Energy Society agency. And yes, we use a gender nuclear data library. This is a result. The reference core shows very short lifetime. This is an infinite multiplication factor because we just use done the pin cell calculation in infinite model. But the criticality decrease rapidly based on their original design. So we check the neutron absorber, which nuclide absorbs neutrons. Of course, fuel material must absorb neutrons to fission. Plutonium is like this. The chloride 35 has rather large neutron absorption fraction, about 10%. And the other comes from salt material. So we'd like to, we change the composition of salt. I mean, we enriched chloride 37. As you can see, chloride 35 exists more about 76%. And this has larger neutron absorption. So we enriched 37 to reduce absorption. Yes, but the effect is limited. We extended burn up this amount only. So it's very difficult to design breeder reactor. And then we change the coolant from salt to liquid metal. Fluoride salt was replaced by sodium because every developed country and Japan has mature technology for sodium reactor. So I use sodium. So then the trend considerably changed like this. It has very high breeding performance, so the reactivity increase with burn up to this amount, to this level. Okay. Why this happened? We checked the neutron spectrum. Red line and the green, orange line is the same. And you can see the blue line. You see the big dip in this energy range. And if you change the coolant fluoride salt to sodium, you have no such dip. This dip was caused by neutron scattering by fluoride 19. Fluoride 19 has very large scattering cross-section in this energy range. So this causes this difference. And this energy range is really important for breeding. You may know the neutron reproduction factor of plutonium-239 increase in this energy region. But if you use fluoride salt as coolant, you lose the important neutrons in this energy range. So you cannot breed. This shows a conversion ratio. This is reference SSR, fluoride 39 enriched core, and the sodium cooled core. The conversion ratio changes like this. And the BANAP also extended. Sorry. And this core can burn some minor actinide, about more than 10 kilogram per gigawatt thermal per year. If you increase the minor actinide concentration in salt, you can increase this number. Then we move to full core calculation. This core is basically based on Japan sodium first reactor. It produces this thermal output, corresponds to 1,050 megawatt electricity. And the core diameter is about 5 meters, and the core height is, we have no change with Moltex original fuel assembly design. So the core height is this number. And we put thick axial blanket, upper, lower, 45 centimeter to improve breeding ratio. Yes. And this is a result. There is one important parameter that is uranium and sodium chloride ratio in blanket region. The reference number is 40%, but the result shows it has very small breeding ratio, only 0.84, and burn-up is 26 gigawatt per ton. So we try to increase the uranium ratio in the blanket salt, 70%, 100%. But still, breeding is not achieved. And the opposite, the burn-up, achievable burn-up, is reduced with increasing uranium ratio in salt. Then we reduce the plutonium enrichment. We can get higher breeding ratio, but we lose burn-up, achievable burn-up. So it's really difficult to design good breeder based on SSR. Why SSR cannot breed? Fluoride salt causes spectrum dip in critical energy range for breeding. One reason. Two, chloride 35 in chloride salt works as plastic absorber, and there was one more negative effect. It produces chloride 36 long-lived activation product. I forgot the precise half-life, but 10,000 years half-life. And this is not small value. So this must be very big problem for the chloride salt type reactor. And the more essential reason is a static salt reactor has smaller fuel volume ratio compared to standard molten salt reactor, because the fuel area is limited inside the cladding. And any fuel salt contains less fuel material than solid fuel per volume. For the fuel pellet for light water reactor contains uranium, 100%, UO2. But the fuel salt contains 40% of fuel salt. So the actinide inventory is less. Smaller actinide inventory in core means less fertile, yes. Less fertile means smaller fissile production. Smaller actinide inventory means less fissile. It needs higher enrichment. Higher enrichment means less fissile, less fertile. And you go back to here. A large leakage effect needs higher enrichment. You have less fertile and come to this same conclusion. So let me conclude. Separated salt, fuel and coolant, separated salt type reactor like SSR and other concept. It was presented in this conference by Andre and I forgot. Anyway, fuel salt and cooled by lead. Such concept was also proposed. And this concept has advantages to limit circulation area of highly activated, contaminated materials. I think this is a very serious problem for molten salt reactor. But this concept can mitigate such problem. However, it shows difficulty in breeding due to less heavy metal inventory with large neutron leakage effect. If thorium is used for this fast spectrum reactor, worse result was estimated. I just calculate this time uranium-plutonium fuel. But the combination of molten salt fuel plus liquid metal coolant should be interesting, attractive concept, but it requires further consideration. Thank you very much.
You considered the changing the coolant salt to chloride.
Yeah.
The chloride, from fluoride moved to chloride and not to molten metal.
I didn't check that yet. You mean the change chloride coolant to?
No,
you said fluoride is fluoride scattering in the change of the spectrum. So if the coolant salt was changed from
fluoride to chloride. Yes, I need to do that, but not yet.
Yeah. About isotopic separation for chloride, what do you suggest?
Sorry, I have no idea. But very easy for just for numerical calculation. Sorry, I have no idea.
Thank you very much for a very nice presentation. I really like it. And at the beginning, when you showed that the closing of the fuel cycle is really important for the sustainability, for the utilization.
Yeah.
I would like to, on this chart, I would like to comment about thermal molten salt reactor. Whenever you have thermal spectrum, you need to clean up the salt very often. So you are reprocessing fuel which has very low burnout. So if your method would be not at least 10 times more efficient than your burnout, so it means you should have 0.01% losses, maybe 0.001% losses, you will not gain a high sustainability thermal rate.
I totally agree. And so I tried fast spectrum concept first. And I'm also checking the thermal breeder, but it has very low burnup and it more leaks to waste stream.
The other point concerning the Moltex strategy, they used to utilize silt cladding at the very beginning. And then they have opened the door at the top in the plenum. They have this opening. What that means that the xenon they produce during burnup is contaminating the coolant. Can you comment something about that? Do you see something about the calculation, any calculation about this effect?
For my calculation, I neglect the such xenon release from pin. Yeah, because Dr. Ian Scott disliked pressurized something, he said. So he want to use this bent type fuel pin. But I don't want to use dirty coolant because we have more difficulty in maintenance or so. If possible, I want to ask Dr. Ian Scott to close this.
In your simulation,
I think the answer is that the xenon comes out as bubbles, so it will immediately rise to the surface of the coolant. And the surface of the coolant is well away from the fuel area, which is the red area.
Mm-hmm.
So there may be xenon present, but it's not in the core.
Mm.
But it's come back. I mean, you have a loop.
No.
Comment here.
in your simulations, did you assume xenon stayed?
Hey, you can take that later. You can take, hang on.
There is a solubility.
Yeah. First here.
In your simulations,
Yes.
did you assume the xenon stayed in the fuel, or did you assume that it left?
I assume it stays in pins inside the pin.
Yes, up there.
Is xenon actually a problem?
What? Pardon?
Is xenon the problem?
I say no, because this is fast spectrum reactor. Accumulation xenon in fuel doesn't affect so much.